but I could name few. So I have named a few. And particularly for my interest and for the within the scope of the talk of today, I would try to touch the smart materials and the functionally graded materials today. When we say smart, then uh, it is to be defined. When we say a person is smart, means his senses uh, are far better than in comparison of its neighborhood. So technically, any system or a material which has built-in or intrinsic sensors, actuators, and control mechanism. So I'm specifying the three components. One is sensor, another is actuator, and third is the control mechanism, whereby means by means of these three components, it is capable of sensing a stimulus. It is the uh, part of sensor, responding to it in a predetermined manner. This is the job of actuator, and to the extent in an appropriate real time. So it is control mechanism, and then reverting to its original state as soon as the stimulus is removed. Uh, for a principal, the smart teacher is the one who sense what the principal is expecting for, does the job, and then reverts to its mean positions. Don't ask anything in response of thereof. Means goes to its original position, and like the same way, the persons, the system, and the materials are called to be smart in the following three major parameters. When we talk about the smart materials, they are of different kind. Firstly, after query, this piezoelectric materials with the invention of the quartz, this started. Then the thermoelectric materials, shape memory alloy, rheological fluids, automobile engineering, magnetostructured materials, and other kind of the varieties are being added day by day, year by year in the class of the smart materials. Out of these, today I will of the piezoelectric material. When we go for the definition of the piezoelectric materials, these materials are those which produce electric field when they go deformation, and they produce the electricity, and when they are exposed to the electric fields, they go under deformation. So this way, first such kind of the material was found, discovered by the Nobel laureate Pierre Curie, and then the piezoelectric effect in the two ways was explained. First is the direct piezoelectric effect. Direct piezoelectric effect is that when this material is compressed, then the voltage difference, this is noted, means electricity is produced. This we call the compression effect. When such material is compressed, then the electric field is generated in the same direction where it is polarized. You can notice the 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 polarization is from this to this direction and negative to positive, and when it is compressed, so compression leads to the polarization in the same. effect. It says that when this crystal is exposed to the electric field, means voltage is applied to this one in the same direction as the polarization is, then the material will expand. And similarly, in this case, the you can notice it is from minus to plus. So the electric field is applied in the direction reverse to the polarization of the crystal. Then this is compressed. So, what is the summary? That for us as a students of physics and mathematics, that when such materials are exposed to electric field, there will be a deformation, and if there is a deformation, there will be a change in the electric field, positive or negative. As I told, the first kind of the piezoelectric material, that was the quartz, and thereafter Rochelle salts and topaz, and then there are man-made materials too, which are the synthetic materials. Among that, the popular two very popular piezoelectric materials are lead zirconate titanate. We briefly called it PZT, and barium titanate. These are the two very common occurring and most used piezoelectric materials in most of the sensors. Uh, so piezoelectricity is not like that, it is found in the crystals only. It is found in the nature also. But due to the paucity of time, I would not be able to touch that component in this lecture. So question comes, what is the utility of such piezoelectric materials? Our class is as vast. We can go for hours and hours to talk about the application of piezoelectric materials. Briefly, where there is a sense, where there is a sensor, there is a piezoelectric material. Be it in the underwater acoustics application, be it any kind of the ultrasonic device, any kind, whether that ultrasonic device is the transducer which the radiologist use as a doctor, or this is the mm, ultrasonic device used by the civil and structural engineers to know the health of the structures of the buildings. Means wherever there is a source and the sensors, there will you will find piezoelectric materials. Nowadays, the flaws and cracks in bridges, in tunnels, in pillars and beams, they are detected with the help of the ultrasonic devices, and the base behind that is the elasticity of the piezoelectric material. Similarly, any kind of the microphone, electric guitars, all works on the uh, with the help of the piezoelectric materials. Similarly, loudspeakers where the electric energy is changed into the sound energy, sound waves, and uh, all pressure sensors or all pressure devices, uh, they based they are based on the inverse piezoelectric effect, which I have just changed. That when there will be a change, the direct piezoelectric effect means when you press them. Say, for example, electric guitar, you press them, the electrical energy is changed into the sound energy. And like this drum, the pressure sensors, which we use in the automobiles and in the lifts, or the energy harvesting. See, around 1976, one concept came, that is That was concept of the harvesting of energy. It means uh, if the piezoelectric motors or piezoelectric equipments are used by using the DC, then more work can be done or energy seems to be multiplied. I'm not saying the fundamental law of conservation of energy is going to be violated, but it seems to be multiplied in the sense that more works it seems to be done. And there, I read that article somewhere in current science, and then I got interested in the field, and I switched to this one. Similarly, the examples of the electronic updiners, accelerometers, phonographs, uh, used in every mobile phone. We know the sensors are there, or the actuators we use in our mobile, this car, all are made up of piezoelectric materials. Uh, yes, this is one of the examples that this piezoelectric motor has changed the size and the usages of the electronic devices. A small motor like this, which is working on the piezo, or that we call it a piezo motor instead of the DC motor or stepper motor, it has changed the total scenario of the electronic devices, because 1/100th of energy is consumed in the piezo motors in comparison to the DC motors, and that already consumes very less in comparison to the AC motors. So piezo sensors, they have changes. So this field is, though piezoelectric materials are not new, but still, due to the smart buildings, due to the smart structures, due to the smart equipments in the automotive industry, their usage is increasing very much. When usage increases, then their requirement increases. It means such materials, they are to be produced, they are to be manufactured in the large quantity. And then it comes that beyond quartz or beyond naturally occurring rochelle salt, uh, the industry has to think about more production for lead zirconate or barium titanate or other sensors appropriate for tailored applications. Before starting the my contribution in this field, very briefly, it is not at all my field because I do not do any kind of the synthesis. I'm not a experimentalist. This disclaimer is there. But I studied what is the process. Process is that any ceramic is that first is the fine powder uh, of the metal oxides. Then that powder, to make it uniform, then this is heated, and thereafter it is again fined, and then a binder, organic matter or some chemicals are mixed to bind that one, and then that matters is heated to bake it, to make it a structure, so that it comes in a crystalline structure, as the brick is made in for house construction purpose. Same way, the ceramics are made in the labs. Same way, but of course in a more controlled mechanism. Then after that cooling, the different shapes of the sensors as per their requirement is given, and thereafter that is polarized, because still it is not a piezoelectric material. Why that is not piezoelectric material? Because state is like this. The dipoles, they have different polarizations. This is here, this is here. So the dipoles of that structure, the ceramic, see, even if I'm talking about the lead zirconate, it shows the piezoelectric behavior, but not in a natural way, not in a natural way like quartz. So for a long time, this material is exposed to the direct electric field such that these dipoles, they are oriented in one direction, in the charged direction. So when this is removed, after that it will not come to the position A. It will more or less, they will be in the orientation, they will be in the orientation where the electric field was applied. This is called polarization, direction of the materials. So now we can think of this material has been manufactured or has been designed, tailored in such a way that in this direction, the main polarity is there, all the dipoles are there. So this body will behave like a charged body. So this is all about it. Here from the role of the other subjects. This is totally a job of the experimental people. The physicists and chemists, they do it frequently in their labs. So uh, now material has been constructed, material has been manufactured. Then question comes, who is going to give the model, who is going to provide the theoretical framework for this model? Here comes the roles of the mathematics, particularly applied mathematics. Oh, so we find a scope here, and that scope can be in the form of mathematical modeling for such materials, to provide the constitutive relations for these materials, then uh, to give the solve the vibration and wave propagation problems. And finally, our job is because to do the crack analysis. Because crack analysis requires exhaustive mathematical calculations uh, that involving the indefinite integrals and the boundary value problems. So here the role of you don't feel it that some mathematics is there because you are using software, but who is providing the algol behind that software? That comes from the mathematical modeling, a forward mathematical modeling on which this inverse works. Basically, mathematical modeling in any of the problem in the real worlds is worked in this manner, that there is some uh, situation, we understand that process, that phenomena, and then after understanding, we see, we write what is there and what is required. It means we try to formulate the real world problem in terms of a mathematical model. That model could be a statistical model, that could be the stochastic model, that could be the dynamic model, that could be any static model, whatever. Then the solution corresponding to that problem is obtained in a mathematical way. Then those solutions are given to the people who works on the data. They test the results, mathematical results, and they try to validate whether it is fitted or not. Or the person who have proposed the model, they do themselves. Try to validate. If it is validated, the results are satisfactory, okay. Otherwise, attempts are made to modify the mathematical model, and this process goes again and again. Once it is validated, then after validations for different situation, then the technology people, then the software people adopt those solutions, make it a sensor, piezoelectric material. There is a built-in a 10% error which is built in the system because I'm neglecting the core space, and could be the micro cracks also. So here we thought of that why should we not give an exact mathematical model for piezoelectric materials when porosity is included. So a class of porous piezoelectric materials was defined, and an attempt was made in the 2006 by me and my students for developing a first a theoretical framework for porous piezoelectric materials. As we are students of mechanics, so we go by the fundamental laws initially to drive the equations. So was here. And when there was nothing, then the first law of thermodynamics that came, that tells us that the uh, change in the internal energy is equal to change in the work done by the sources and change in the heat, plus or minus consumed or released into the system, delta Q or delta W. So we started from this fundamental law, and we know the this change in the internal energy in any elastic body. We know this is equal to stress into rate of strain. That is, stress is one are the electric forces, another is the mechanical forces. So for mechanical forces means the stresses are deformation. The change in the internal energy is contributed by the sigma ij and d epsilon ij. And we know from the Gibbs free energy, the concept of the Gibbs free energy, that the change in the internal energy due to the electrical forces, that would be equal to EI into DDI, where EI is the electric field and DI stands for the electric displacement. So work done will be like this. Okay, so this is not our work. This is known, earlier known. It means the piezoelectric materials, the change in the internal energy, which I am taking for the purpose of here in particular form, the strain energy. So du is written as sigma ij and d epsilon ij plus ei di. Now, what happens in the case of the porous piezoelectric materials? A porous materials has two phase. One is this phase, this is solid, and one is this phase where the fluid is there. So it means porous materials are biphasic material. And if they are biphasic, then it will be the stress in both the phases, displacement in both the phases, electric field in both the phases, and electric displacement in the both the phases. So we applied this equation and we accordingly we modified the strain energy, that is equal to sigma ij d epsilon ij and sigma star and d epsilon star. The star is corresponding to the fluid phase, so this term is added into this strain energy expression due to the liquid phase. Similarly, EI star, DDI star, which is coming from the work done by the electric forces by with the electric displacement DI star in the fluid phase of the material. So this equation was modified as like this. After modification, then enthalpy function was found, calculated, and W was found as the internal energy minus the work done by the electric forces, EI DI and EI star DI star. I'm using tensorial notation instead of the vector notation. So if you are habitual of using the vector notation, then it is E dot G dot product of E and D, and similarly E star and D star, like that. So dW, after computing this, we got it that this is sigma ij d epsilon ij d star d epsilon ij di di and di star di. So this is the final equations which we got it. We all know from the internal strain energy function that when we differentiate the strain energy with respect to strain components, we get the stresses by again from the first law of thermodynamics. So when we differentiate curly W, this partial derivative of W with respect to epsilon ij, we get stress component in solid phase. Similarly, partial derivative of capital W with epsilon star give us sigma star, and similarly here the electric displacement and in phases solid and liquid. So this equation we were able to write in the forms of electric displacement, and finally the whole of the expression, this 2W, we were able to write in the forms of the deformation tensor, means in the forms of the epsilon ij, epsilon star, this E electric field Ek and electric field Ek star, which are usually measurable quantities. So this way, knowing this, what we can do, if we again differentiate it, we will find the Cij. Every student of applied mathematics and physics, they know what the CIJKL stands for. This stands for the stiffness matrix, और इसी का particular जो form है वो Lami's constants, यानी जिसको आप Young's modulus या modulus of rigidity कहते हैं. These are the particular forms of this generalized stiffness matrix. Means CIJKL describes the elastic behavior of any material. Similarly, this Mij describes the interaction between the solid and fluid phase of the porous material. Similarly, we will get the Eijk. This third order tensor uh, are called piezoelectric coefficient. Piezoelectric coefficients tells us that how much electric field will be generated when a force sigma ij or deformation Eij is there in the material. And zeta ijk is the piezoelectric coefficients in the fluid phase, and this xi ij and this aij, they are the dielectric coefficients of the material. So we can avoid the purely theoretical mathematics. I just can give the glimpse that finally we obtained this mathematical equation, and differentiating it, we could get this relation, and that lead to the constitutive equation. We know constitutive equations are the equations which constitutes a model. So this model, which theoretically was told that how much stress sigma ij will be generated when there is a strain epsilon kl and epsilon star in the fluid phase, electric field ek and electric field ek star in the liquid phase. Similarly, it gives us the stress in liquid phase. A di gives the electric displacement in the solid phase, and di star gives the displacement. So all the theory, all the formulas starts from this equation sigma ij, whose simplest form, in the one-dimensional form you use in the lab, that is sigma is equal to E into capital E into small e. That is very simplest forms of the Hooke's law is. This is the 2.11 but this you are seeing, this is the generalized forms of the Hooke's law and Fourier law. अब ये theoretical था. Then next question is, doubt ourselves, is this the equations which we have obtained, are they justifying all kind of the mechanism which could be possible in this complex structure? Yes. What could be the interaction? The interaction between stress and strain. This is being explained by the elastic coefficientCijkl. They are appearing here. Okay, fine. Strain and electric field, behavior of the piezoelectricity, explained by Eijk. This is there. Fine, very fine. Then, as the piezoelectric materials, they do have the dielectric character, then this dielectric coefficients of these xi ij, they are there, means relation between d and a. So within one phase, all the four interactive process and then d2 stress, this is given by the Eijkl, means piezoelectric components, that is there. Similarly, all these interaction in there. Up solid and fluid phase, they do not work in isolation. Means the dilatation in the one phase should cause the stress in the other, and similarly the pressure of the one should cause the strain in the solid phase. So these interaction are also taken into account by the tensor M, this by zeta ijk and by this dielectric factor A, capital Aij. So all possible interaction we could able to map and then to give it that finally that this is there. And to complete the work, the next job was to provide the equations of motions for such materials, and that comes from the Newton's second law, or we used Hamiltonian mechanics, and based on that we calculated the L, the Hamiltonian kinetic energy minus this work done W, and finally after a lot of calculations, all might not be interested in this, they are available in the papers. So finally, this equation of motion, after doing lot of mathematics, were obtained. So in this way, we could do it for the equation of motions. They could be derived. Then, uh, as we are students of mathematics, we love to prove the results in the abstract forms of the mathematics. So theorems. So we tried it. So we know there are two fundamental results. Uh, One is the reciprocal theorem. Reciprocal theorem says that there are two systems, one system interacting with the two by the virtual displacement, say for example u1, delta u1, that would exactly be the same, effect would be the same which the second system exert on the first. I'm not writing in terms of the mathematics, basic law I'm telling it. This is called, in the mechanics, this is called dynamical reciprocal theorem. So that next job was to prove the dynamical reciprocal theorems with the invented model. We could prove it, but as it is totally mathematical rigorous, so I'm avoiding it. Now, next fundamental result was that to check whether the results of this model will be unique or not, it means whether the uniqueness theorem will be satisfied or not, that we considered the two system and we proved the uniqueness, and finally we got that the solutions are unique. It means go ahead. So this was the first paper, this which came in the Journal of Sound and Vibration, and this theory of porous piezoelectric materials was first proposed by me and our student, and thereafter a lot of more than 235 citations of this single papers are there. It has been used mainly by engineers and physicists thereafter. So, but our job was to validate our model, that how this will behave. That we know uh, Mendelian theory also gives us another alternate way to give the constitutive equation. Then we thought कि हम मिडलिन थ्योरी में प्लेट थ्योरी से वेरीफाई करके प्रॉब्लम को करके देखते हैं और फिर देखते हैं कि क्या ये सॉल्यूशन सेम आते हैं, दो वी वर श्योर. So we did this plate problem. It is just like the vibration in the two-dimensional plate. Then it requires a lot of mathematics in terms of the series solutions. We did it like this. Lot of calculations are done, computational as well as the theoretical one. So after solving this mathematical problem, what we could get, just I will come to the result because time is less. Yes, yeah. The vibration mode system, we are getting same equations as we got theoretically in the first problem. So after that, it was sure that the mathematical model which has been provided to the for porous piezoelectric materials, that is correct. And then the next problems we undertook, that then basically sensors are used for waves propagation problems. So next step was to give the theory of wave propagation in porous piezoelectric materials. Then we considered this. This is the portion which we have already formulated as our model. Then we took the equation of motion. We solve the equation of motion in the forms of the by way of the harmonic analysis, means we seek the solution in the forms of the waves, and then do again a lot of mathematics to solve this. वो सारा मैं बड़ा सिंपल सा करके बताने की कोशिश कर रहा हूँ कि we get a system like this WB is equal to 0. W is a matrix, 6 by 6, B is a vector of 6 by 1, then this system is there. And everybody knows that this system will have a non-trivial solution. If we put B is equal to 0, then it will always be satisfied. But non-trivial solution will exist if the determinant of the coefficient matrix is equal to 0. This is the necessary and sufficient condition. So this was put, and after expanding it, we got this equation. So this h bar, this variable is the 1 by v, and v is the velocity. The problem is not so simple because T1, T2, T3, T4, T5, these are the complex coefficient because viscosity has been included. And the problem with any transcendental or any algebraic equation with the complex coefficient is that we have to deal them very cautiously, because even simple problems are not solved by the big softwares like the MATLAB and MathCAD, etc. So we solved it one by one. We the physics and chemistry and applied mathematics people know these are the different crystal classes which are mainly, I'm taking the popular one, though these are 32 classes. I'm not mentioning all them one. The crystal classes for which we have done the solution, I'm mentioning only those. One was the monoclinic, this is the journal one, else then triclinic. And monoclinic, both kind of the symmetry, that is M stands for the mirror symmetry, and monoclinic 2 stands for the symmetric about the x2 axis. And similarly, orthotropic materials like 2mm and 222, and tetragonal material of 4, and hexagonal. This is the most, you can say the most simple model is the 6mm, that is hexagonal symmetry. So, by using these two experimental papers of Gupta and Venkatesh, we took the data of the coefficients for this, and we finally got the solutions of the waves in the forms of this. Now, we can see these because sensors are used in two different domains. High frequency means when we are using for the ultrasonic, the range is in the megahertz, and when we are using for, say, underwater acoustics, the frequency is less, then it is in the low frequency range. So we have computed the results and behavior in both the frequency domains separately, and they are different also. We can see from the figures. This is for the low frequency, and you can see this solid curve is for the case when non-piezo porous is there. Means when we reduce, when we neglect the piezoelectric effect from the porous material, then this curve will be obtained, and this velocity curves, they match with the existing velocities of the porous materials when piezoelectric effect was not there. So for the validation of our results, these solid curves are shown, and they matches with the existing literature. And the difference between this dashed and the this dotted curves from the solid curves, that shows that how the variation, how the behavior will get changed when piezoelectricity is included in the model, which is actually there as far as P and this SV waves are concerned. So that gives the reason that why this advanced model should be used. Similarly, as we are using the porous piezoelectric material instead of the piezoelectric material, so it was honest to us that how the porosity will affect the velocity structure or velocities of the waves in this way. So that we have shown here, that with the change of the porosity, means if it is 20% and 40% and 60%, it is impractical to talk about 80% because it will nowhere go. Mainly it remains between 10 to 30%. So in this range, we can see there is a great appreciable change, variation in the velocities of the waves which propagate in such smart materials, and the change in this up to the range of the 30%, that is very appreciable. So regions against the results were motivating and encouraging to see go ahead with this model. Then we presented it that how the porosity will affect in the case of the most general class, that is class of the crystal class of M, when there is symmetry only in the one coordinate plane. So uh, after then it was we know that in case of the uh, orthotropic, transversely isotropic, or triclinic or monoclinic materials, the wave velocity depends on the direction. It is not independent of direction. It is not like that material will behave the same when it is the incident rays comes from any direction. It will not behave so. It will not respond in the same direction, same way. It is certainly not. So these are the direction dependent, and the direction dependency of the phase velocities, these are very much clear from these three-dimensional plots of the phase velocity, where we have changed the theta and phi longitude and latitudes, and to show that how the wave velocity of the four waves they will. This is something very interesting, that V2, that is the slow wave, which is due to the solid phase in the porous piezoelectric material, and this V4 is corresponding to the charge propagating in the forms of the wave solutions, that is phi, electric potential phi, its velocity. So these two results, that is V2 and V4, they were different, and they are new. Similarly, these are the results for the class 2. They are more or less same. But you see how this results and this results, they are different just by changing the symmetry, that is from monoclinic to trigonal class. The result is changed significantly. It means piezoelectric behaviors, the sensors are going to behave differently what their elastic orientation is. It means we have to be conscious while characterizing the elastic properties of the crystals so formed. Every crystal formed in the lab that cannot be treated as 2 mm, or that cannot be obviously treated as 6 mm, that if the predecessors has used it. Here we have shown the effects of viscosity in this class, and as expected, the wave velocity decreases for all the four waves when the viscosity effect was included in the class B, and when viscosity and high frequency both were taken into consideration, we can notice the second wave, the second sound wave, that shows a significant noticeable variation towards the increment. In this one, it means this wave is going to be significant as far as this ultrasonic waves are concerned. So we have to give the importance to this negligible part. Negligible in the sense that this velocity is 9,000 meter per second, and here it is 2.4, even less than one third of this one, hardly detectable. But in the high frequency range, this becomes important. We have to taken into considerations. Similarly, the effect of the piezoelectricity is shown in the forms of the graph, that what will happen if material is taken as porous piezoelectric, or material is taken as the piezoelectric only. So porosity is going to make the model so accurate, that is seen by this difference between the PEM and PPM. Similarly, we can notice the change between the PEM. PEM stands for piezoelectric material, means usual sensors. And ppm is showing the results by taking into consideration our model that we are terming it as ppm, porous piezoelectric materials. And the changes are noticeable, recognizable, hence that gives similarly for the class 6 we see the effects as the degree of symmetry is as far as barium titanate and lead zirconate is concerned. Here, this difference in the model is affecting a considerable amount, and here is the effect due to the porosity. So, when the porosity is increased from 10 to 30%, notice a change. It means from all the directions we can conclude that number one, sensors which have built-in porosity take into account, and we have proved that the by taking the proposed and verified model of porous piezoelectric materials, the results are considerably and appreciably uh, changed for the wave propagation and the vibration problems. Hence, the next sum steps that it is for the technologist to adopt these expressions there in the models while revising the softwares for that. So this is all we have done. Just at the end, I will end the lecture by a quote. These are the references that see, today is the era when we have to come out of ourselves the boxes of the comfortability. Those who can do the marvelous work in their domains, appreciable, nothing wrong. But doing a productive work by remaining in the vertical channel of the same specialization, same subject altogether, uh, it sometimes becomes difficult. Then expand your views, expand your interaction with the other subjects, then some good results comes out. This is what we have experienced after taking this project into consideration. Thank you from my side. Any query, please?
Isha ma'am.
Good afternoon, sir. Sir, am I audible?
Yeah,
Sir,
please.
I want to ask the question that how can advancement in piezoelectric materials contribute to sustainable energy solutions?
Yeah, very good question. You see, I have told you one sustainable energy is that when we are using the piezoelectric materials, we are saving the energy, as I have given already one example in the case of the piezo motors and DC motors, right? Secondly, in many of the countries, you might have noticed that, say, just like toll places in our country, they do have some kilometer bands, right? So then behind the first layer of the road, they put the piezoelectric sensor layers for certain kilometers. Heavy vehicles passes through, vertical load is applied on those ones, and that produces the electricity, just utilizing the effect. You might have seen in the toys that you press it, the bulb goes on, LED starts. Yes, just like it. Basic basis is the same, that there is a compression, there is going to be a light, means the electricity is going to be generated. Second concept came this for the sustainability, that uh, you you ignite a parallel of the sensors, put them in a vertical channel, give the vibration by 1 1. Now that vibration will vibrate the other plates, means apply the forces on them. Then electricity is produced in the parallel circuits. So that concept was named as energy harvesting, means we are applying one force to the one plate, and then that plate sets the other piezoelectric plate into the vibrations, and energy comes multifold. Then they are put in a parallel circuit, and then the energy is stored in the forms of the capacitors. So this is the way of the concept of the energy harvesting is there. It's a concept somewhere in the Germany it is being practiced. But certainly, I'm hopeful someday technology people will take the idea, and we will have the change of the energy into the energy different from solar energy, otherwise also.
Thank you, sir. Got it, sir. Thank you so much.
Thank you, sir. It was a very knowledgeable and productive session with you. We would surely like to listen you more on other topics also whenever we will get the opportunity. Thank you so much, sir.
Thank you.
Thank you, sir. Now I, Manchula, from Department of Chemistry, would introduce our keynote speaker, Emeritus Scientist CSIR, Professor S.P. Khatkar. Dr. S.P. Khatkar, sir, was born on 1st November 1959 in Mokhra village of Rohtak. Sir was professor and former head of Department of Chemistry, MDU. Sir has been awarded with the designation of Emeritus Scientist CSIR. Sir has held various prestigious positions, some of which are Head, Department of Chemistry, MDU, Chairman of Central Purchase Committee, MDU, Director, University Industrialize in MDU, Member of Academic Council, MDU, and many more. Sir has been active in the research field since 1981 and guiding many PhD and MPhil students. His prominent research fields are